Hey, what's up, guys? So today we're going to be doing find median from data stream. It's a hard question, a good concept question. So I think it's important to do something like this type of question because it uses like heap. Heap is nothing but a priority queue. So there are two types of heap: max heap, min heap. Very simple. Do not get confused by the name. It's just priority queue. One is priority queue and another one is reverse priority queue. That's it, right? So where does heap shine? Well, heap shine in log n insertion and deletion. So this is insertion, this is also deletion, but one main point is, for example, in max heap, you can find the max element in O1 time, right? And in min heap, you can find this again in O1 time, the min element, max element, right? So these are very important properties. So priority queue inside is just arranged like I believe like like a binary tree. That's where we are getting this login time from. Um, if I'm not fully sure, is it binary search tree or is it just a binary tree? So let's see. Is priority queue a binary search tree? Um, so it's a binary heap instead of a BST. So it's basically implemented using arrays. So, yep, similar concept. So that's why you get it like these things, heaps are like binary. That's why they have this tree structure kind of stuff, like can separate out, branch out, and are easy to find in log n time. Because with every branch you probably take is you are getting rid of like log and stuff. If there are like 10 branches, I take this, 9 branches gone, something like that. So for BSTs, there are just 2 branches only. So with like one branch, 50% out, another branch, 50% out. So in that way, this is like similar concept. Okay. So instead of going into the implementation details, which is not necessary, I just wanted to give you an idea of how they're implemented inside so that you have some kind of sort of reasoning of what's going on and why we should be using heap. All right. So the question says very important stuff. Ordered. It has to be ordered in teacher list because if it is not ordered right, um, then you can do this question just with a list and then just check for even and odd and return accordingly. That would make this question easy, right? The brute force way is again super easy again. So there are two brute force ways. Either you can sort your list in the add nums method, or you can sort your list in the find median method. So these are just brute force ways of doing it. It will give you correct answer every time. But sorting takes n log n time. So we cannot sometimes afford n log n. So right now, what we are going to be doing is instead, we are going to doing add nums in log n time and this in O1 time. So this is probably the best you can ever like get in an algorithm. If you see log n, usually it's not possible to do O1. You know, any algorithmic problem that is non-deterministic, that is, there doesn't really exist a math formula for it. You need to search somehow, then it's log n. Never you can do better than log n. As far as I am aware, I don't know any algorithm that does it. Maybe if you find it, you can win Nobel Prize. Anyways, so basically there are two heaps, max and min heap, right? Now with the max heap, we just want to store elements in the reverse order. So I just had a new class because in C sharps you cannot do in Java like collections dot reverse order. So I just created this new class, made my own comparator, and compared these two things. Okay, so that sounds good to me, right? Doesn't take too much. So what our logic is, say we have elements 1, 2, 3, 4. Okay, say they are in some weird order. So let's just say 4, 1, 3, 2. Okay. So what I'm saying is there's this max heap, there's this min heap, Okay. In the max heap, I just want to put the first element in the max heap. Okay, so 4. Now, as soon as I put it inside here, I just want to dequeue the maximum element and put in our min heap. Because what sort of logic we want to maintain is that every element in the max heap is less than equal to min heap. So what this logic allows us that in the end, that the element of max heap, if it's equal to min heap, then you can just take the max heap max element, min heap min element, and divide by 2. That would be your answer. Okay, so let's just see this example. So first I do max heap, I dequeue it, put it in a min heap, and then I say if min heap count is still greater than max heap count, dequeue this to put it in here. Okay, so 4 is in our max heap. Next comes 1. I put 1 here, then I say in the max heap I want to dequeue my element. Now you might be saying DQ1, but that's wrong. You don't need to DQ1, you need to DQ4. It's a max heap, right? Taking max element, put it inside the min heap. Cool. Now they have the same length, so this if condition will never execute. Okay, so now this much is clear. Okay, now I want to add a 3. Okay, so I take a 3 and I say to 3, okay, I want to DQ you, put you in here, and then it says, okay, but my min heap count is greater than my max heap count. So take out the minimum element in the min heap by saying DQ, because O1 access to minimum element stored at the top. That's why it's minimum access. Put it back here. So we have 1 and 3 here. Cool. So now I put a 2 because next insert was 2. With this 2, I'm gonna DQ from my max heap because dequeuing is needed to maintain it, but what I want to say is like 3 is getting dequeued because max element, right? Put it in our min heap, count is equal. So they're sorted now. So actually they would be in this order. So 3 and 4. Okay, so 1 and 2. So what I'm trying to say is in the max heap, the top element is 2. And in the min heap, the top element is 3, right? These are the root nodes. That's why they have that O1 axis, because you go the first element guaranteed to be in max heap to be the maximum element in min heap, guaranteed to be the minimum and the min. Cool. So now once we have this, well, then what can we do? Okay, so since they are equal, that means this if there are two things that are equal in size, right? They always have to be even. Two numbers that are equal will always add to even, right? 5 plus 5, 10, 6 plus 6, 12. That's both the cases we needed. For our, there's only 2 cases. Both odd, both even, both are coming out to even. So that means all I can do is just take this element, top element, take min heap top element, add them, and then divide by 2, because that's the median formula. Answer is 2.5. Great. But what happens if max heap is actually greater? Well, if max heap is greater, say max heap length was 2, min heap length was 1, then in that case, I just return the max heap peak. And the reason because of this is this both are odd in length, okay? Odd length means you need to take the middle element. Now I am saying that since this is less than equal to every element in min, that means if this is the case, then 2 needs to be there. But if there was 2 in here, then still needs to be 2, because we are saying less than equal to, and we are saying that max heap can contain the more number of elements. So it has to be 2. So that's also the reason we are not saying that if min heap dot count is greater than max heap, because what we have structured at add now, we have making sure that never happens. So with this, two conditions becomes O1 simply. This becomes O of log n. And even if you want to see how many log operation we are doing, is we are doing one log operation here. We are doing one log operation here. We are doing one log operation here. And then we are doing one more log operation here, and then one more log operation here. Now you can definitely reduce this. You can make this in 3 log operations. So that's simple exercise. I'll leave it up to you. But if you still cannot figure that out, let me know. You can basically, what I'm trying to say is combine these. Even in C sharp, you can do that. So in C sharp, what happens is this is the number, the first one, and second one is its priority. Just to make it more clear, I had written out in this way, but you can do it basically in 3 log n and O1. And since we do not consider this factors, we just get removed, remove it, boom, gone. And this would be the question. So pretty good question, pretty interesting question, very important concept. And yep, that was it for the video. I'll see you guys next time. Peace.